All right, what we want to do in this lecture is look at some examples of partial fraction expansion. So the first thing we want to look at are examples that involve real roots that are not repeated. So in this example, the denominator has already been factored. So we have 3 terms in the denominator, and then we have a numerator. So what we do first is we assume that this can be written by separating out the denominator terms. So we will have some a over s plus b over s plus 2 plus c over s plus 3. And then that's going to equal our original function. And so our job here is to solve for a, b, and c. So the first thing to do is to multiply through by the denominator, and then to eliminate the denominator because it will be common on both sides. So when you do that, you get s squared plus 12 is a times s plus 2, s plus 3, b times s, s plus 3, and c times s, s plus 2. And then the way to solve for a, b, and c, the easiest way is to pick values of s that will make a lot of terms go to 0. So if you pick the actual roots themselves, so first let's pick s equal to 0. Notice that makes the b and c term go to 0, and leaves us with the equation 12 is equal to 6a, which makes it easy to solve for a. So a is equal to 2. So if we then pick the roots of -2 and -3 respectively, and I'm sorry, this is a typo, this should be an s. If we pick that respectively, then we can solve for b and c. And then, so basically, once we have a, b, and c, we just substitute into this. So f of s can be written as 2 over s minus 8 over s plus 2 plus 7 over s plus 3. And the only thing you have to be careful of here is to be sure that you assign the proper numerator term with the proper denominator term. All right, so the next thing to look at is an example of real repeated roots. So in this case, we have a numerator, which we're going to the only reason to look at the numerator is to make sure that its order is lower than the denominator. So I have a denominator of order 4, a numerator of order 2, so I'm fine to use partial fraction expansion. So here's what I was talking about in the earlier video, where we have a second order pole. So first of all, we'll take our first term, a over s, and then we'll take b over s plus 1. And then we're going to start with a squared term. So we'll have c over s plus 2 squared, and then we'll start with the single term d over s plus 2. The reason you have to do this is you don't know when this rational function was constructed. You don't know if you had only s plus 2 squared terms or s plus 2. So it's possible that this could have been constructed out of an expansion that looks like this. So we need to take advantage of that and write all 4 of these terms. So solving for a, b, and c are fairly straightforward because once again we can pick the roots, the root of 0, the root of -1, and the root of -2, and when we do that we get the following expression. But now the question is how to get d. The easiest thing to do is to just pick any value and pick a value that makes the numbers work out easily. So I chose s equals -3, and when I did that I got this equation, and now I've already solved for a, b, and c, so I can substitute in for those. When you do that, in this case, you get d is equal to 13. So here is that expression rewritten, and notice I just flipped my s plus 2 and s plus 2 squared, the order in which those were written, but the coefficients in the numerator are correct. Okay, well there's an alternative to this, and it's referred to as the method of equating coefficients, or the algebraic method. In this case, we take our partial fraction expansion and we multiply out all the terms and eliminate the denominator because it's the same on both sides. And so we end up with this expression, except now instead of making substitutions for s, what we're going to do is we're going to multiply out the entire set of terms So when we do that and we multiply these polynomials together, we get the following expression. So remembering that because of this equality, what's on the right hand side has to equal what's on the left hand side. And that has to be true term by term. So whatever the constant is on the left hand side, which is 4, is going to have to be the constant on the right hand side. So if we look through the right hand side, we see that we only have one constant term. So what we do first is we look at the constant, or the s to the 0 power terms, and we'll have 4 on the left hand side and 4a on the right hand side. And now we look at the terms in s. We have 0 on the left hand side, but we have 8a on the right hand side, 4b on the right hand side, c on the right hand side, and 2d. So we write that as an expression. So once again, we're just selecting terms in s. We then do the same thing for s squared and s cubed, and what we end up with now are 4 equations and 4 unknowns. So you could solve the equations simultaneously, and if you do that, you should get exactly the same result that we got in the previous example.